Good afternoon, everybody. My name is Benjamin Chaya, and I'm a PhD student from the University of Amsterdam. And today I will be moderating the 10th webinar of the CompBioMed Webinar series. Today's webinar will be given by Dr. John McCullough from the University College London, where he is a postdoctoral research associate within the Center of Computational Science. I would like to remind everybody that these webinar series is run in collaboration with the VPH Institute, and that the recording of today's webinar will be posted on the CompBioMed website. So without further ado, I give the floor to John.
Great, thank you very much, Ben. So welcome everyone to this webinar. So today I'm going to be talking about the HemeLB software that's being developed to model cardiovascular flows at UCL. So if we look at a human body, hopefully everyone is well aware that these are very complex systems with a number of different interacting systems that all work in a unified way to make us operate and live our daily lives. You have all the different organs within your body. You have your lungs, your heart, your liver, your kidneys, your muscles. All of these things have been tailored to complete a specific job in the operation of your physiology. There's the blood vessels, which are transporting blood throughout your body, and there's the skeleton, which is supporting all of these in the structural way. And so all of these interacting systems are interacting in a way that is by no means trivial. And the performance of this system is complicated by a number of factors that is unique to an individual. So this could include age, gender, lifestyle factors, personal choices to do with diet, for example, genetics. All of these things can contribute to how different people react individually to different influences on their daily life. And so many medical treatments that doctors need to prescribe to treat someone can be influenced by all of these factors. And so doctors are forced to take into account all of these individual complications in order to make the best decision for a patient. And so a question that doctors have to ask themselves is, how can outcomes for these patients be improved? And so one way that we as scientists can assist clinicians is to help them better understand how some given course of treatment can impact a given individual, and how the best course of treatment can be chosen for an individual. And so how do we propose to do this? Well, we propose to do this by creating a digital replica of an individual based on their own personal circumstances, and use that to be able to investigate how different possible treatment options would manifest themselves, and how effective they would be in treating a given individual. So other benefits of this approach are that clinicians can recommend a course of treatment with the great confidence that it will work well for that patient. Patients have a better understanding about what's actually going to happen to them. The treating doctors, the clinicians, can show them exactly ahead of time what's going to happen to them. And indeed, the digital models that we can create can provide information about a given patient that wouldn't traditionally be available to doctors. So how would we go about constructing a digital human? So there's been various medical scanning technologies that have been developing since the 1970s largely, and probably the most famous ones of these, and the most well-known and the most widely used, are computer tomography scans, or CT scans, and MRI scans, or magnetic resonance imaging. And so these two approaches use slightly different techniques to construct images of the internals of a human body. They have different benefits for soft tissue and harder tissue, depending on what's wanting to be analysed. But these allow for models of a an individual human to be constructed based on their individual anatomy and their individual physiology. And because of the long-term development of these tools, both the quality of images that are able to be obtained from them and also the cost of these things are both improving more and more, enabling us to be making a digital replica of a human an achievable task. So with this virtual human, what does it need to have, particularly from a numerical perspective? So what we need to do is to develop numerical codes that represent the individual components of the body that I highlighted earlier. So for example, the blood flow through the vessels of a human, how the heart pumps that blood, but also how the electromechanical mechanisms that are going on to actually cause the heart to beat. There's the transfer of oxygen in the lungs and how the lungs expand and contract with the movement of the diaphragm. The different components of how a brain works, for example. All of these are complex systems and are best dealt with using codes that are specifically targeted to those different situations. A lot of the behavior on a human scale occurs at multiple different length scales. So you've got structural behavior of how bones, for example, in the femur, which is several tens of centimeters long, you've got blood moving through the vessels. So the narrow capillaries are on the order of microns, whereas the aorta coming out of the heart may be the diameter of your finger. So you've got different scales that you're trying to analyze, all of which have their own complications. When you've got multiple different codes replicating different parts of the physiology, these need to be able to communicate together. So information that's being pumped out of the heart needs to be passed to the vessels. Some information of how oxygen is moving into the lungs needs to be passed into the blood flow. All of these need to occur in an efficient way, but also need to be done in a physiologically meaningful way. When resolving these different components, it needs to be done in a high enough manner that's actually meaningful for clinicians to make a decision on. And ultimately, the time it takes to simulate a human physiology actually in operation, the time it takes for these simulations needs to actually be in a reasonable time frame. There's no point having to wait multiple weeks in order to get a simulation. You want this to be done ultimately in terms of minutes, at most hours. So for any listeners who are not part of the CompBioMed project, the project has put together a YouTube video that discusses how a virtual human can be constructed and the benefits it can provide at the YouTube link that's on this slide. So we want to model a full human, and so that means using, at least in current specifications, some of the largest supercomputers that are currently available. So if you look at your the computers that are in your phones, for example, they might have 4 cores in them, for example. The largest supercomputers that are currently available have tens of millions of cores. So, and many other machines have order of several hundreds of thousands of cores. And so this is a significant amount of both computing power and also computing speed. So the typical measurement of computing speed is floating point operations per second. So this is basically how many little calculations can a computer do every second. And it is reckoned that in order to start modeling a full human is requiring exascale machines, which is order of 10 to the 18 floating point operations per second. And the machines that are able to achieve this are anticipated to be in the next generation of large-scale supercomputers, anticipated in the next 2 or 3 years at current schedules. Okay, so now we need to actually do these simulations of full humans. So as I mentioned before, to simulate a full human, you need to use machines of this scale and performance capability. So not only is the actual computing task and conducting these simulations a challenge, also is developing codes that perform efficiently at this scale. This raises many computational science questions, such as how is information communicated across all those hundreds of thousands of cores? How are those cores able to share their load in an even way? And indeed, another significant question is, once we have run a simulation, how do we actually view that data in a way that makes decisions meaningful and makes that information that we've generated understandable to a human, not just a computer science specialist, but also a medical specialist or indeed a patient. So one of the advantages of computers increasing performance is that smaller scale models are increasingly being able to be conducted using desktop-based machines. And this is especially becoming more and more true with GPU acceleration, so using graphics processors to speed up scientific computations. And making codes work on such hardware is another computational complication that needs to be taken into account as both codes move forward and also as how future supercomputers are architected. Okay, so moving on to the actual subject of today's talk, HemeLB. So what is HemeLB? So HemeLB is a code that has been developed to model the blood flow within humans, particularly focusing on the vascular problems and being optimized to deal with these. So why is studying blood flow a good starting point for the virtual human? So it's basically that in both a physiological and a computational or virtual human, the blood flow is what transports information, be that oxygen or numerical information, between the different components of your body. You have blood moving from the heart, being oxygenated in the lungs, and transferring that oxygen throughout the body. And so knowing and understanding how that blood flow moves throughout the body is a key physiological concern. And so as different models are developed for the heart, the brain, the lungs, for example, HemeLB would be an interconnect between all of these operating within a full virtual human. HemeLB itself, the first published version was made available in 2008, and then over the last 10 or 11 years it has been developed by various different people from different institutions around the world, and has been shown to perform well on computing infrastructures throughout Europe and also in the US. So from a technical standpoint, HemeLB is a C++ code that has been parallelized with MPI. It is currently only a CPU code, but that is something that future work is hoping to take advantage of GPU processing powers. It's a fluid flow solver that uses the Lattice Boltzmann method to solve fluid flow. And within this Lattice Boltzmann method, there's multiple boundary conditions available that can capture different interactions at the ends of a vascular system. And one of the key advantages of HemeLB is that it has been optimized to deal with the sparse geometries that are characteristic of vascular systems. So what do I mean by sparse geometries? Well, if you take a bounding box around the domain that you're simulating, if you're doing that for a straight cylinder or a cube flow, for example, then most of that domain is going to be fluid flow that you're interested in. However, if you do the same thing over a vascular network, most of the space in that domain is stuff that you're not interested in. The actual vessels that you're trying to model occupy a very small percentage often less than 1% of the actual domain bounds. And so being able to deal with this much empty space means that the HemeLB code has to be optimized to deal with that specifically. And the code execution has been shown to scale well on up to hundreds of thousands of cores. So it has successfully been able to do this on sparse geometries as well. So where has HemeLB been used? So HemeLB has a number of past applications, including designing stents for aneurysms, for capturing how blood flows in the tiny vessels located in the retina. It has been used to study flow through vessels in the brain, and has been used to investigate magnetic drug targeting, where a magnetically responsive treatment is coded onto to magnetic particles, and so an external magnetic field is used to guide those particles towards a target area. So, for example, if you had a tumor, which is what this image on the right here is showing. So if you had a tumor site, for example, here that you're trying to treat with medication in the bloodstream, you can have the particles injected and use a magnetic field to guide as many of them into this area of interest as possible. And so HemeLB has the capability to study those sorts of problems. So another example of work that's been done with HemeLB has been the development of an interactive pipeline for studying aneurysms. And so if we have a patient, who has some sort of aneurysm in their brain, for example, then using medical scanning technology, we can get an idea of the location and the geometry of that area of interest. Then we can start converting that to files that can be run in a simulation. And so we can run a simulation. And so in a interactive loop using computational steering with clinicians, we can study the flow through different parts of the domain, looking at it from different angles, looking at different external or different flow properties that are of interest. And so if people want to look at that in a different way or make some slight modification, then the idea is that part of this loop, you're able to make those on the fly and have a more intuitive understanding of what's happening within the flow. So this is part of some ongoing work, but it uses CUDA to actually visualize these things in real time. So this allows different properties to be shown that may not necessarily be able to be obtained in a conventional medical setting. So for example, the pressure that's actually located in different areas throughout a aneurysm that's want to be treated, shear stress. So shear stress is basically a shearing force that's acting across the wall of a vessel, and this has been identified as a potential cause of aneurysm rupture. And so identifying areas of high shear stress, particularly in proximity to an aneurysm, can identify whether it's at risk of rupture and how urgent further treatment of that aneurysm may be. And also, for example, the velocity of particles, velocity of flow through the simulation. And so because numerical models are able to generate a whole lot of different outputs that may not necessarily be traditional for medical personnel, discussions are ongoing with clinicians to actually help them in identifying what information would help them make better decisions for the patient. So just about to show a video, assuming that technology does its thing. So what this video will show is blood flow through a circle of Willis. So the circle of Willis is a vascular feature that's located at the base of the brain. And so this is a rendering of a HemeLB flow through that geometry. So these are just some tracer particles that have been added to the flow. And you can see how these are being transported through the geometry. So you can see that there's multiple inlets and outlets here, but also that the HemeLB simulation is able to capture the tortuous geometry of this vascular structure in a way that enables the flow to be visualized quite clearly. Okay, and so the still that we have there on the screen is actually of that same geometry, but showing a more static representation of flow through that system. Okay, so HemeLB uses the Lattice-Boltzmann method, and at this point it's probably fair to me to give a brief introduction to the technique for those who are not familiar with it. For those who wish to learn more, one of the previous CompBioMed webinars was conducted by Jonas Latt from Geneva, looking at HemeLB specifically, not HemeLB, the Lattice-Boltzmann method rather specifically, but there are also multiple textbooks that are available on the subject. So again, this is meant to be a brief introduction to Lattice-Boltzmann, and hopefully not here to labor the point too heavily of how the various mathematical techniques and scientific issues that are related with this system, with this technique. Okay, so what is the Lattice-Boltzmann method? It is a numerical method for solving the Boltzmann equation, which under certain specific conditions of flow speed and assumptions based on equilibrium, allows it to solve the Navier-Stokes equations for fluid flow. And so these are the mathematical equations that govern how fluid moves through any given geometry. So the Lattice-Boltzmann technique has a localized algorithm, which means that at different points in space, it's able to update itself just based on the information that is there. It doesn't need to communicate to the outside world or to other locations. This makes it very easy to parallelize, which is good for execution on these large-scale supercomputers that I was talking about previously. The implementation of it means that it is able to capture the complex boundary shapes, particularly those that are present in vascular geometries in a straightforward way. And modifying this algorithm allows for various different complicated flow physics to be able to be captured. So multi-phase behavior, multi-component behavior, non-Newtonian behavior, thermal behavior, all of these are able to be captured using the Lattice-Boltzmann technique with slight modifications of this localized algorithm. Okay, so where do we start with the Lattice-Boltzmann technique? We start by determining what lattice structure we're going to use. So if we're using a 2D or a 3D simulation, and when I say velocity directions, what I'm talking about is how many of its neighboring cells and or itself is a given site passing information to and from. So for example, a D2Q9 lattice, which is a very widely used lattice, has 2 dimensions where it's studying in, so it's a 2D flow, and it communicates in 9 velocity directions. So for example, if we're looking at this point here, the 9 would refer to the 8 surrounding it, plus itself. So if we're wanting to study a complicated, study our domain, we firstly discretize this domain into different nodal locations using a Cartesian grid. So as is highlighted on this sketch here, we have some pipe with curved boundaries. We overlay a Cartesian grid across that, and we have nodal locations that capture that shape. And so we then identify what are our fluid sites and what are our wall sites. So in this model, at a very coarse resolution, the yellow dots represent the fluid sites, the green dots represent walls, and the blue and red dots represent different parts of the inlets and outlets. Okay, so once we set up our domain in that manner, we assign what's called distribution functions to each point. And so these represent the probability of fluid at that location moving in a given velocity direction at some point in time. And so how the Lattice-Boltzmann equation evolves over time is that these are relaxed towards an appropriate equilibrium function. And so often this is taken as some numerical approximation of a Maxwell-Boltzmann distribution, but other options may be available. But this is the one that's typically used in studies. Okay, and so now we've set up our domain, we've set up our distributions. How do we evolve this through time? And so this is a two-step process of streaming and collision. So let's start with the collision process. So HemeLB typically uses what's called a BGK collision function, initials of its original authors back in, who first proposed this idea of a single relaxation time back in the 50s. So this was capitalized on when Lattice Boltzmann techniques first started coming into being in the late 80s into the early 90s. And so what it does is that it takes a distribution function and then relaxes it towards an equilibrium based on some relaxation time. And so the BGK uses a single relaxation time. There are different options for doing this that have multiple relaxation times available. But what this does is it basically governs how fast or how much does a given velocity distribution change when compared to an equilibrium. Okay, and so once we have those updated values, we need to stream them to their neighbors. So in this cycle, we've done the collision function, and so now we have our distribution functions that have been reevaluated after the collision, and now they need to be streamed. And so from this central point here, we have each moving out in their indicated direction to the stream point, and this is occurring at all points around our domain. And so, for example, we'll have a velocity coming from here back down to our central node, one coming from on the right here back to the central, and there'll be one velocity in the indicated in the appropriate direction coming back to the central node. So it has its new 9 velocities there, and these are at the next step updated with the collision process yet again. And so this loop is updated over and over again throughout the simulation to allow it to progress. Okay, so with the Lattice-Boltzmann method, because you store the distributions at a location, you need to do something to actually get the macroscopic behaviors that mean something to us as scientists and as humans in general. So, and in Lattice-Boltzmann, this is done through a summation technique called moments. And so in Lattice-Boltzmann, the first moment gives you density. The second moment, which is here Ci represents the vector pointing in the given velocity directions. And so summation of population distributions multiplied by this velocity vector will give you your momentum vector. And so then dividing your momentum vector by your density vector will give you the velocity vector at each point. You're also able, using the second moment, to calculate the stress tensor that's acting at each point locally. So in order for the Lattice-Boltzmann equation to represent Navier-Stokes equation, it is only valid in what's called the low Mach number limit. So only when the velocity of the flow is low compared to the local speed of sound. And so a consequence of this is a relationship that occurs between viscosity, the relaxation parameter of the BGK, and the discretization of your domain. And so this equation is what kind of governs your parameters that you set into your simulation. So your viscosity is usually set by whatever fluid that you're trying to model, be that blood, be that water, be that oil, be that air, for example. The discretization and the time step are set again often by the parameters that you're trying to solve, and then you can determine a relaxation parameter that you wish to use. Indeed, the Lattice-Boltzmann literature indicates that the value of tau of approximately 1 often gives the most accurate results, and so that you can use this to impose a time step or a grid spacing depending on what other problem parameters that you're trying to deal with. Okay, and so finally, boundary conditions. So when I indicated streaming before, each node communicated information out to its neighbors. When you're on the edge of your domain, you have populations that are unknown coming into you from outside the domain. And so the art of Lattice-Boltzmann boundary conditions is to construct these unknown values in some way to represent a boundary, the desired boundary condition, be that a wall in some description, or be that, for example, a pressure outlet or a pressure inlet, or a velocity condition, so with fluid being forced in at some velocity. All of these are possible within HemeLB. Okay, so a bit of an outline on how HemeLB has been shown to perform on large-scale computers. So this is a graph showing scaling performance on the Blue Waters machine in the US. And so when we're trying to outline how we're trying to judge the performance of a code, so this is doing a strong scaling test. And what that means is that you take a geometry of a given size, sufficient size, and then you add more and more processes or cores to that problem in order to solve it faster. And then you plot how the speed up of that simulation takes as you increase the number of cores. And so on this machine, each node has 16 cores. And so when we're up here at 18 and 21,000 cores, 21,000 nodes rather, you're looking at approximately 300,000 cores, give or take. So this is a very large scale simulation. And so we can see up to that about 288,000 core mark, HemeLB is working very well. And this is a significant result to be able to perform at this level, at this number of cores. And this tail off at the end, that's some of the non-ideal performance that's part of the challenge at working at very high number of cores, is you need to firstly be able to evenly balance how work is distributed among those cores. You need to be able to input and output information efficiently. You need to be able to communicate between different nodes efficiently. When you're starting to use the full quantity of cores in a machine, which was the case in these larger simulations, you're always bound by your slowest processor. So if you have one core, one node, one processor that's not working as well for some reason, then that's going to provide a bottleneck to your overall performance. Okay, so now I'd like to work through a bit of an example of how to actually run a simulation with HemeLB. So HemeLB has been designed to run on these larger cluster machines, so machines with large numbers of cores, either university scale clusters up to the large national clusters that have hundreds of thousands of cores. That said, it is able to be run on laptops with a Unix-based environment. So if you use a Linux or a Mac machine, then this is native to your machine. If you're using a Windows 10 machine, then investigate the Windows subsystem for Linux. This provides a Unix type portal that you're able to operate within on a Windows machine. On earlier versions of Windows, unfortunately, this capability is not available. The HemeLB setup and operation does require familiarity with command line operations. So actually installing and compiling the code, so general tools for compilation, so CMake, MPI, a C++ compiler, pretty standard. The actual specific dependencies for HemeLB can be installed as part of the actual compilation of the code. So if you have a look online, so we're currently constructing a new HemeLB website, which should be coming online very shortly. And so more information about installation, compilation, and running code will be available on that site. And so when you actually come to compile the code, the actual LatticeBoltzmann parameters relating to your collision kernel, your boundary conditions, and the lattice that you're using, these are set into the compilation of the problem, and the actual geometry information that you're trying to solve a simulation for comes into the input files, which we'll look at shortly. So as I noted before, installation instructions as well as some examples will be available on the website once it becomes live. Okay, so the example simulation that I wanted to work on is looking at flow through a bifurcation that's being driven by a pressure gradient. And so in this problem, we will have a elevated pressure at the single inlet with a lower pressure on the split outlets, driving flow through this domain. Okay, and so in a input XML file, we have a whole bunch of information that relate to the simulation. So we have our Lattice-Boltzmann parameters. So there's our step length, that's our time step resolution. We have the number of steps we want to run our simulation for. We have the discretization of our domain, so the delta x. And so these two parameters in relation to the viscosity of blood, which is what HemeLB is set up to solve with, can give you the tau parameter that you're solving with. Here we're pointing to the GMY file, which is the HemeLB input file for describing geometries. And here we describe our initial conditions. So how is our simulation domain set up to start with? And it's being set up with a pressure at a constant pressure throughout the domain. Moving further down the file, we have our inlet and outlet boundary conditions. And so we have our pressure condition at the inlet at a value of 0.001 and a value of 0 at our outlet. So we have that pressure gradient acting across the domain, driving flow through it. Keen-eyed watchers will notice that there's this is a cosine condition, but with the amplitude parameters and the periodic conditions, meaning that we have a constant pressure being applied. But you can choose different values here to have an oscillatory pressure within the bounds of Lattice-Boltzmann driving this flow if you wanted to do a more complicated boundary condition, for example. Similarly, with the outlet conditions, we have a constant pressure being prescribed and the location of those outlets also being indicated there. The final part of the input file is describing how we want to output information. So HemeLB has a number of options available, but two that have been selected here are the whole domain. So this will output information on pressure and velocity at each node throughout the domain every 100 steps. And so this is a output statement that should be used with some caution, because if you have a large domain, this can get very large very quickly. What's more useful is to be able to target your output to get specific information at a specific location. And so just as an example here, we have the inlets. So this is just outputting information that's available at the inlets of the domain, again being output every 100 steps. Okay, and so now we can launch our simulation using an MPI run command. The number of nodes that we wish to run our simulation on, or the number of cores rather. We have pointing to the HemeLB executable. We provide the input file and we point to where we want our outputs to go. And so once you launch this simulation, the HemeLB output will look something like this, with some information about setting up the simulation and then some periodic output to show that the simulation is progressing, with some statistics of interest that can show whether a simulation is behaving as you wish it to. So this simulation that was being conducted, it took 8 minutes on my desktop computer using n = 4. so just 4 cores, and this has just over 2 million sites to the problem. So it's a fairly substantial problem, but by no means the largest that we've conducted. Okay, so once you complete the simulation, you need to actually convert that data to something that is human readable. So the DAT files that are indicated in the input file, they have a lot of data, but they're compressed in a binary format that's not human readable. And so the first tool that's provided with HemeLB is the HemeExtract tool. And so this converts it from the DAT file format into a text file, which makes it human readable. So these files list the nodal locations within your specified region, and then the outputs that you wanted, so pressure and velocity in this case. The ParaView toolkit is a widely used visualization package that if people have been involved in scientific computing for a while, they've probably seen it in some form or another. And so this bash script converts the readable output file, which is a dump of all the information that you've output, and splits it up into time step files, which is more useful for the ParaView input. Okay, so if you haven't used ParaView before, so these are some fairly explicit instructions on how to do a basic visualization. If you're more familiar with ParaView, feel free, if you're working with HemeLB in your own time, to investigate further how to visualize data in different ways. Okay, so first you need to import your files using the standard file opening techniques. And so you want to open the one that is indicated by group. And so this allows you to open all the time step files into ParaView simultaneously. And then to apply it, you need to click on a green button that's located here. So ParaView is designed to work with very large data sets. So in order to do that, it gives you a chance to double check your parameters before you ask it to do a big job. And so that's what that apply button that's located there allows you to do. Okay, and so now we have the information in, we need to convert it to a more useful form. So ParaView defaults to reading in delimited data in a text file using a comma. What comes out of HemeLB happens to be done with the space. So in the box down the bottom here, you need to change the default comma to a space, and then you can click the green apply button. And so then you'll have output that looks like this. And so we have the grid points, the pressure and velocity parameters. Okay, so now we can start moving this into a more useful form. If we go up to filters in the top menu and you go alphabetical, then look for tables by points. And this will convert a table of data, which is what we've read into ParaView, into a grid point set of grid points that can be visualized within ParaView. And so in the bottom here, we just need to tell it which is our X, Y, and Z coordinates, which are grid X, grid Y, and grid Z. And then again, click the green apply button. And so finally, let's show some sort of data to it. So if we click on the gray screen, which is the render screen, you can, and then in the pipeline on the left here, if you click the eye that's next to table of points, you'll see a set of white dots. And then so if you change that from the visualization format from solid color to Z velocity, for example, you can see these points at the inlet colored by the Z velocity. And you can use the time step functions to play those as a movie or step individually through different steps. So the HemeLB the ParaView toolkit rather is a very powerful visualization toolkit. There's a lot of options and a lot of tools available within it. So this example is by no means the limit of its capabilities. There's certainly plenty more that can be done with it. And if you haven't used ParaView before and want to be doing visualization of scientific data, then by all means, I encourage you to investigate further into its capabilities and capacities. Okay, so as a bit of a summary of where HemeLB is going to be heading into the future. So as a code, both as computers get larger and more capability within that compute power is opened up, HemeLB is a code that's constantly developing. Indeed, the accuracy of results and the scalability of performance is always a concern. And so ongoing work includes coupling it to other physiological codes, representing the elastic behavior of vessels within HemeLB, being able to capture that behavior, and indeed working to make HemeLB take advantage of GPU implementations, because this allows faster simulations to be done on smaller machines, but it is also an accelerated technology that is being deployed in more and more high-performance computing systems. So it is of HemeLB's interest to take advantage of that where and if it is able to. So HemeLB, as I've discussed through today, is a numerical code that's been designed for solving blood flows, particularly on human scale vasculatures. It has been optimized to study sparse geometries and has been shown to scale well on hundreds of thousands of cores. It has demonstrated capability in a number of complex flow situations and will be something that enables communication of multiple organ simulations in a model of a full virtual human. So again, the HemeLB website should be coming online very shortly, and I encourage you to have a look at that when it does come out. So as always, these projects don't get funded, don't get done on their own, and there's been a lot of funding that's been provided to it over an extended period of time, and a lot of postdoctoral workers and PhD workers along the way that have contributed to its development. Here's some select publications if people are interested in reading further about what HemeLB has done in the scientific environment. Image references if people are interested. So that's enough speaking from me, and if you have any questions about this this talk, please raise them with Ben and we can discuss those shortly.
Thank you very much for such a nice talk, John. So yeah, right now is the questions session. So if anybody has any questions, please write them in the questions tab and I will read them out loud for everybody and for Jonathan to answer. So right now, I see no questions posed. So I actually have a question myself for you, Jonathan, John.
Sure.
The bifurcation that you have shown in your example.
Yes.
What was the physical size of such a geometry? You gave it in the amount of Lattice Boltzmann nodes in the domain, but what's the physical size of that bifurcation?
That's an excellent question. Off the top of my head, okay, so the resolution is 550 microns there, I believe. My conversions work correctly. I guess the best way to actually look at it is if we go to this result here. So each of those dots that you can see on there is a single nodal location within that geometry. So you're probably looking at, let's say, 20 or 30 dots across the radius as an example. So we're probably looking at order of, what's that, 20, so
maybe this is like sub-millimeter scale.
That would sound about right, yes. So okay. Do we have a radius? Not in these inlet conditions. In terms of inlets and outlets, we're looking Z direction, so it's about 370 lattice units along its length. So 370 times that value, whatever that turns out to be. So okay. Order a few centimeters thereabouts, or yeah, order millimeter scale in that problem. So You're looking at the scale of a small blood vessel.
Okay. I just wanted to understand, like if I was a general user, if I wanted to study something like a cerebral aneurysm or something like a bifurcation, say in the circle of Willis, I just wanted to understand maybe the performance. So would I probably need somewhere on the order of 10 to 20 nodes on a cluster, or 10 to 20 cores to simulate something like that?
Okay, so as a starting point, the actual physical size of a domain that you're trying to simulate isn't really of relevance. It's more how that compares to the lattice spacing. So with a, where's our picture? So if we have a domain like this, it could easily be order meters across there, but you just choose your grid spacing so it resolves this this opening to the level of accuracy you desire. As I indicated before, when I was going through here, so this simulation, which has 2 million lattice sites throughout that domain, that was n equals 4 cores. So that could be done on a laptop in on the order of 10 minutes or so. So that size simulation, you want, it can be done small scale. If you're looking at problems that have hundreds of millions of cores, hundreds of millions of lattice sites, then you'd be looking at needing a multiple nodes on some sort of computing infrastructure, be that a university cluster or be that a large scale high performance computer. If you're wanting to do a very high scale model that has 1 billion nodes, for example, then you'd be looking at very large machines with large numbers of cores to run that efficiently.
Okay, thank you for such a concise answer. We do have one question from Peter Coveney, and he writes, you wrote about coupling of HemeLB to coupling within HemeLB. Could you elaborate on that?
Yes, okay, so within a human body, you have two networks of vasculature systems. You have your arteries and you have your veins. See if I can find a picture that I can talk to you a bit more clearly here. Okay, so for example, here you've got your arteries in red and the veins in blue. So these are two segregated networks in a way, in a manner of speaking. And so one part of the coupling that we've done with HemeLB is not just to external physiological codes, such as for a heart or a lung model, for example, but also to HemeLB itself. So enabling blood to travel in a full circuit from being pumped out of the heart through the arteries, experience some sort of pressure drop as it goes through the capillaries, then being resolved as it goes back through the veins into the heart again. And so HemeLB, we have it coupled to itself in order to have both the arteries and veins being able to be captured within a single simulation.
Okay, thank you. That's clear. For that, I believe that is all of the questions that I have seen posed in the questions tab. So I think that brings this webinar to a close. So I would just like to thank everybody for their participation and listening, and for John for giving such a great presentation. I just want to remind everybody that this webinar will be posted on the CompBioMed website. So if you happen to miss something, you can go back and watch the recording of this presentation. So with that, I'd just like to thank you one more time, John, for a great presentation.
Thank you, Ben, and thank you everyone for attending today.
Yeah, thank you. And with that, I will close this session of the CompBioMed webinar series. So thank you, everybody, and have a nice afternoon.